Okay. So as we have discussed, there are three approaches for enforcing mutual exclusion, and these three approaches are termed as software approaches, special purpose machine instruction, some hardware support is there, and then finally operating system or programming language support. And we'll pick each and every approach in detail, and let's see what are the pros and cons of each and every approach. Now, software approaches are divided into various attempts while they were building the solution to provide mutual exclusion. And as I told you that when you are providing mutual exclusion, then some conditions must be followed. Only one process at a time is allowed in its critical section. Process, if it is halting in its non-critical section, must do so without interfering with other process. There should be no deadlock or starvation. If no other process is inside its critical section, then a process must not be delayed access to the critical section. There are no assumptions to be made about relative process speeds or number of process, and process remains in its critical section for finite time only. So there are three approaches, as I told you: software approach, special purpose machine instruction, OS or programming language support. Software approach, the first attempt is very naive attempt. A process will always check whether it can enter the critical section or not, and process is doing this again and again. Suppose it is not allowed to enter the critical section, then it will be checking and then again waiting, checking and again waiting. That's why this term busy waiting is utilized. Processes can do nothing productive until it gets permission to enter its critical section. So I am giving you this code where there is a turn variable, and let me switch to the whiteboard. So there is a turn variable, and which is global. Turn is shared between process P0 and P1. Now can anybody explain me this code? What is happening? And whether we are able to provide mutual exclusion or not? Anybody?
So, sir, when sir, first of all,
Suppose turn is initialized. We have to initialize the turn. Turn is initialized to 0.
yes, sir. So when the turn is equal to 0, suppose P naught is executing first. So the while loop, since the value of turn is equal to 0, so the while loop will not execute, and
Mm.
it will shift to the critical section, and
Okay.
P naught will enter the critical section.
Okay.
So to achieve mutual exclusion, we'll check if P1 process is also not entering the critical.
Suppose P0 is here only.
Yes, sir.
P0 is inside its critical section,
Yes,
and P1 tries to enter.
yes, sir. So
So
when P1 tries to enter, the value of turn will be 0, and so it will be
it will
looping
be
in
doing
a
nothing.
inside loop.
It
Yes,
will do nothing.
it will do.
Okay. So while turn equal to 0, do nothing. It is not doing anything. Fine. It will be there in the loop only. Got the point? Again. So P1 cannot enter when P0 is inside critical section. That is okay? Okay, Vigyan?
Yes, sir.
Okay. Now later on P0 comes out and it will make turn equal to 1. At this point of time, now P1 can enter. Yes or no?
Yes, sir.
Now at this point of time, P1 can enter. So this solution ensures mutual exclusion. There is no issue. mutual exclusion is ensured, it is enforced. Any problem you see in this solution?
Yes, sir.
Yeah.
So what if there isn't any interrupt between the critical section? Means let's say we have two instruction in the critical section, and while we are performing the first instruction, and then there is an interrupt come from the operating system. Then
And P naught leaves.
yes, sir.
That's what you
But
are saying.
but yes, sir.
This you cannot do anything. So if you see the slides properly, we have discussed halting outside critical section. Fine. If a process that halts in its non-critical section, that should not make any effect. Fine. If a process is halting, or you are saying it is moving out of CPU, what I am saying, suppose it is killed here. So you cannot do anything. Fine. Because process is inside critical section and process is not executing, process is not progressing, then we cannot do anything. So that is okay. Yeah, your point is well taken. Another problem?
No, sir. I mean, it doesn't provide mutual exclusion. My point is that.
Okay, we want to say that. So
Yes, sir.
how it is not providing mutual exclusion?
So let's say our critical section is consist of two instruction, right?
Okay.
And we want that P naught should perform both the instruction, then it should move to the another process P1, right? But what if I perform the one instruction only, and then there is an interrupt come,
Hmm.
then I can't able to perform the second instruction,
Hmm.
and my operating system switches from P naught to P1,
Hmm.
then my expected result will be different from the actual.
That I have
So
already taken example. That is, even if you have mutual exclusion, fine. So the thing is, even if it is switched to P1, can P1 do anything?
No, sir, because turn has not changed.
Yeah, P1
Oh,
cannot do. Miss one instruction, two instruction, 20 instruction inside critical section. We have made everything as a critical section. Even if you are interrupted and things are switched to P1, can P1 enter? Because P1 is dependent upon this turn. Turn is 0 right now. So until unless this critical section is completed, turn cannot be changed. And until unless turn is changed from 0 to 1, P1 cannot do anything. Is it clear to everybody?
yes, sir.
so I have one doubt.
Yeah.
So उस केस में सिस्टम हैंग नहीं हो जाएगा जैसे अगर प्रोसेस P1 पे स्विच हो गया एंड while loop will continue because
Mm-hmm. While loop will continue.
sorry.
while while condition is not true, no?
So we are wasting CPU cycles on P1 if the
Yeah,
turn is
that's
not
there.
done.
That's there. That's there. That's the name is busy waiting, no? Hmm. That's there. Busy waiting, no? We are waiting and we are busy. Wasting CPU cycle. And mind you, it is first attempt only. Okay. You are not hitting the bullseye.
Sir, if the value of turn is 0,
01 नहीं होगा तो
Huh?
yes sir.
sir, if the value of turn is 0 and we are in the while loop of P1,
Hmm.
we cannot get out of it until P0 is executed.
Yeah, that's the point. Now here the problem is P naught. Suppose P naught is scheduled 10 times in a given time. Hmm? So P1 can only execute at the max 10 times in that given time. Are you getting my point or not? Because until unless P naught executes, P1 cannot get a chance. So the relative speed or relative number of execution of one process is affecting another process. Is this okay to everybody? Because P1 can only execute when P0. Actually, it has to be alternate. P0, P1, then P0, then P1, then P0, then P1, and so on. Now P0, suppose, has executed, and P0 want to execute again. Cannot. Before P0 can execute again, P1 has to execute. Yes or no?
Yes, sir.
So that's what is the issue here. Shared variable turn indicates who is allowed to enter next. Can enter if turn equal to me. An exit point variable to other process. There's a deadlock if other process never enters. Suppose P1 is never scheduled. Fine. Suppose P1 is never scheduled. So P0 is kind of completed, and next time it will be just waiting. Okay? Because it is dependent upon P1 to change the value of turn again. This solution, yeah.
Sir, if P1 is executing
Hmm.
and we have scheduled P0 for the next time or maybe
Hmm.
another time. But sir, after a particular time pointer is finished, won't P1 be halted again by the CPU?
Give me the situation first.
So
Let me open my whiteboard. Yes, what you are saying, P1 is executing. Where?
so P1 is execute means P1 is
In its
requiring the attention of
in
CPU.
its critical section or out critical section. So always when we talk this in this terminology, so there would be entry to critical section and exit to critical section, and there is a critical section. So where the P1 is executing, first of all, you need to point out that.
So P1 is executing in its critical section.
So P1 is here, yes. Okay, then P1 is timed out.
Yes, it is executing and the loop is infinite.
No,
Since the
P1 is timed out. P1 is timed out. Okay.
yeah, what happens after it is timed out?
After it is timed out, what happens? P1 is in its critical section, no? So suppose critical section is having 10 instructions. Okay.
Yes.
So P1 is interrupted here. Okay. So next time when P1 enter, remember, P1 will start from where it has left. P1 need not check again. Are you getting the point? It's a piece of code which P1 has to execute. Yes or no?
Yes, sir. So the
Hmm.
context memory will be so.
Obviously. So you are confused. You are thinking that P1 has to again come back here, huh? And
Yes.
execute while. No, P1 has done its job. No? Hmm. Yes. So as I was telling you, pace of execution is dictated. Solution guarantees mutual exclusion. There is a problem of busy waiting, as you people have rightly pointed out. Pace of execution is dictated by slower of the two process. Means if P1 execute 2 times, then P0 will execute 2 times. So it's not like that one process can execute many time, and another process can execute less time. It would be, they are completely interlocked. If one process fails, other is permanently blocked. Wherever it fails, inside critical section we don't care because that's not a condition, precondition for us. But even if one process fails outside its critical section, other process will be permanently blocked. If it is failed, suppose initially it's failed, then it will not be able to change the turn variable, and other process will be permanently blocked. So this was the issue in the first approach. Now let's see the second attempt. Each process can examine the other's status but cannot alter it. When a process wants to enter the critical section, it checks the other process first. If no other process is in the critical section, it sets its status for the critical section. So here what we are doing, we are declaring a Boolean vector flag where flag 0 corresponds to P0 and flag 1 corresponds to P1. And we have enumerated this Boolean variable, Boolean array as false equal to 0 and true equal to 1. For example, Boolean flag 2, 0, 1. Initialized to 0, 0. Both are initialized to false. So instead of turn variable, we have taken one flag, Boolean vector, where false is 0 and true is 1. And this Boolean vector is initialized to false, false. Now let's examine this solution. Yes, any comments? Flag, both flag are initialized to false.
Sir, I think
Anybody?
mutual exclusion will be achieved.
You think that mutual exclusion will be achieved?
Yes, sir.
How?
So, first of all, if both are initialized to 0, flag
Mm-hmm.
1 and flag 0,
Mm-hmm.
so when we'll enter process 0, so
Mm-hmm.
it will not enter this while loop. It will and set the flag 0 variable to true. So, and then enter the critical section. And in process 1, if it starts executing, then while flag 0 has been initialized to now true, so it will do nothing for that time. And
Okay. You are
after,
missing one very important point. Who is this speaking?
sir, began.
Abhigyan. Abhigyan, there is a problem here. Fine. Let me take the. Fine. There is an issue here. Now, actually, I'm saying that mutual exclusion is not provided. Means this particular can fail in providing mutual exclusion. Now, both are false. Both flag 1 and suppose P0 runs first line. And this is the process you need to follow to debug the codes, the process I am discussing. So this would be false, and while condition will not be true, and P0 comes here. At this particular time, there is a switch, and P1 gets a chance. Before flag 0 can be made true, P1 gets a chance. So flag 0 is false. P1 can also enter. Both will make now again switch. Now P0 can run. P0 can make it true. Now again switch. P1 can make it true. Both can enter critical section. And then both can make false. If we have switching just after one instruction. So we need to check like this. So there is a condition if we have switching like this, one instruction after each instruction, if we have a switching process switch, then mutual exclusion will not be provided. Is it okay, Abhigyan?
Yes, sir.
So the problem with this solution is that mutual exclusion may not be provided in one or two situations. This message does not guarantee mutual exclusion. In some situations, suppose P0 runs 2 or 3 instructions continuously, then it may be provided, but it does not guarantee the mutual exclusion. Each process can check the flags and then proceed to enter the critical section at the same time if switching is like that. Problem with the second attempt. A process can change its state after other process has checked it, but before the other process can enter its critical section. A process can change its state. Process can change its state after other process has checked it, but before the other process can enter its critical section. So what is the solution? Set flag to enter critical section before checking other process. If another process in the critical section, when the flag is set, the process is blocked until the other process releases the critical section. So what about this? We have done nothing. We have moved this instruction at the beginning. Okay. Yes, anybody?
Sir, if sir, when we enter P0 and flag zero's value is set to true, and then after that process one is executed and flag one value is set to true, so then both processes will not be able to.
Yes. So there is a problem here. If P0 executes this instruction, then P1 execute this instruction. Then if P0 execute this, it will be blocked. And if P1 this, it will be blocked. Both are blocked. So both will not be able to enter. That's what you are trying to say?
Yes, sir.
Okay. So let's see what is the problem here. Deadlock is possible when two processes set their flags to enter the critical section. Now each process must wait for the other process to release the critical section. Problems of third attempt, process sets its state without knowing the state of the other process. Solution. Now the solution is very interesting. A process sets its flag to indicate its desire to enter the critical section, but it is prepared to reset the flag also if it finds that somebody else is already there. Other processes are checked. If they are in the critical region, the flag is reset and later set to indicate the desire to enter the critical section. This is repeated until the process can enter the critical region. So instead of setting its own state to be true, it is declaring its desire that I want to enter critical section. Bhai sab log theek thaak ho, If it is okay, then I can enter. If it is not okay, I'm prepared to wait. This is what is the. I have to take this call. Just a minute. Okay, and this will be repeated until the process can enter the critical region. See here, and give me your comments. Yes, Karimullah, can you explain?
Sir, I'm thinking.
The rule of thumb is switch after each instruction. Anybody else? Aman?
I'm thinking I've not got the exact version.
Okay, let us do this. Let us do this. Suppose P0 gets a chance, executes this. Flag 0 would be true. And afterwards, P1 gets a chance, flag 1 would be true. Again, P0 gets a chance, flag 1 is true. While flag 1 is true, you enter inside, you make yourself false and enter into random delay. Delay means you are just sleeping for a while. So P1 gets a chance, executes while. Right now it is false. While loop will not run, P1 can enter its critical section. P1 can enter its critical section. P1 is executing inside its critical section. P0 is in delay. Suppose delay is over. What P0 will do? P0 will make flag 0 equal to true. P1 is still in its critical section. Flag 1 is still true. Because P1 is in its critical section. So this while loop will keep on executing. False, delay, true, false, delay, true. Later on, when P1's critical section is complete, Flag 1 will be false. P not get a chance, and P not enter into critical section. Any comments?
सर अगर सारे इंस्ट्रक्शन एक साथ ही रन करें, मतलब P1 और P0 दोनों के, मतलब वो रैंडम डिले अगर ना हो तो थर्ड अटेम्प्ट जैसा ही हो जाएगा।
अगर डिले भी बराबर हो, स्लीपिंग टाइम भी, तो क्या हो जाएगा? दोनों इकट्ठे आ पाएंगे अंदर? ये चेक करो। थर्ड अटेम्प्ट में तो डेडलॉक हो रहा था, इसमें डेडलॉक हो पाएगा क्या? Look, there is a difference. In third attempt, if you see carefully, in third attempt, there is a possibility of deadlock where no process can progress. And here, this random delay can, even if it is equal, it will not be equal for all the time. Every time you run this for loop, this while loop, you'll be picking up a random delay in both processes. So this will result in live lock. So it's not deadlock, it's a live lock, which can be broken. Fine. It is possible for each process to set their flag, check other process, reset their flag, wait for the delay, again set their flag, again reset their flag. This scenario will not last very long. So in any case, it is not a deadlock. Deadlock means there is no way ahead, way forward, though there is no way forward. But still, this is undesirable. So in this solution, everything is fine, but there is a possibility of a live lock. Is it okay to everybody? Brajendra?
Yes, sir. Got that. Yes.
सर हम लाइव लॉक उसी को कह रहे हैं ना सर, जो फ्लैग 0 फॉल्स के बाद जो डिले उसी टाइम पे अगर P1 पे
Look,
एग्जीक्यूट
there
हो
is a
तो
difference between deadlock and live lock. They can be in a lock step, but if somehow one process get a chance, this live lock may be broken. There is a chance to break this lock.
ये सर इसमें टाइम का पता नहीं है, लेकिन इवेंचुअली वो कभी ना कभी
break हो जाएगा. There is a chance to break the lock. In previous solution, there was no chance to break the lock. That's why it was deadlock. So even if live lock is there and you can proceed ahead after some time, but this scenario is undesirable because you will be eating up the resources unnecessarily. But it's better than that third attempt where it was deadlock. Now I'll show you the attempt of Peterson. This is the correct solution, and what we are doing, we are initializing both flags to false, and this is a construct for executing both processes parallelly, bar begin P0 and P1, where there is a turn variable also, fine, which is again a global variable, fine. So Boolean flag 2 in turn, fine. Flag 0 is initialized to false, flag 1 is initialized to false. You can initialize turn also to anything, 0 or 1. Fine, because you need to initialize turn. And now see the solution. I'm giving you 5 minutes. Think over it. Okay, let's check. Let's check P naught. While true, okay, so it is true. So what we'll do flag 0 equal to true, okay, flag 0 will be true. Suppose switch, flag 1 is true, again switch, turn equal to 1, again switch, turn equal to 0, again switch. So right now turn equal to 0, fine, flag 0 equal to true and flag 1 equal to true, and control is here. So while flag 1 equal to true, yes, flag 1 is true, and turn equal to 1, but turn equal to 0. So this will not be executed. P naught can enter critical section. If P naught in its critical section and switch is there, while flag equal to true, yes, flag 0 equal to true, and turn equal to 0, turn equal to 0, do nothing. P1 is blocked here. So P1 will keep on coming and checking it. Later on, flag equal to 0 would be false. And then if a switch is made, again come here, flag 0 is false and turn equal to 0. This condition is not satisfied. P1 can enter critical section, and so on and so forth. So this is the correct solution. Any comments?
Still the problem, busy scheduling will be there.
Busy waiting will be there. So this whole set of solutions are busy. Busy waiting would be there in a majority of the solutions. Because if something is locked, you need to go and check the lock. Yes or no?
Yes, sir.
Apart from busy waiting, the deadlock, live lock, mutual exclusion enforcement. Just check. Can you run P naught again? P naught again after P naught without running P1? Check, Brijendra, that P naught get a chance, and again P naught is scheduled.
Okay, sir.
Abhigyan, everybody else check. Can we run P naught again and again without running P1?
Yes, sir.
Yes.
Yes, sir. Yes, sir. We can run.
So there is
Yes.
no dependency, no?
Yes, sir.
Yes, sir. It will,
There is no dependency like the first attempt. Okay. So we have checked all the corners actually. Okay. Now one question is out for the examination. Fine. I'll ask one question based on these four attempt and correct solution. One question will come where you need to either write a code or a code will be given to you. You need to check that code and ensure that everything is fine. You can make a note in your notebook that one question will come from this, whatever examination you will be appearing. Any more doubts to anybody? Okay, if there are no doubts, then we can move ahead. So, as we have seen, it is difficult to write a code by ourselves because they are difficult to debug. So there are other approaches to provide mutual exclusion, and most straightforward is the hardware support. One is interrupt disabling. A process runs until it invokes an operating system service or until it is interrupted. If a process is running continuously, mutual exclusion will be guaranteed. If you disable all the interrupt, mutual exclusion will be guaranteed. The problem of mutual exclusion is only when you allow many processes to be executing, half executing, executing and leaving and things like that. If you give a processor to a process until unless it is completed, it cannot be interrupted. You just mask the interrupts, disable the interrupts, then it will be guaranteeing mutual exclusion. But this is a very, very bad approach. If there is a single processor, the processor will be limited in its ability to interleave the programs. Multi-programming will not be possible. At a time, only one process, kind of sequential. One process get the thing done, another process done, another process done. So interleaving is not possible and you'll be wasting so many CPU cycles. And in any case, it is difficult to achieve in multi-processor, multi-core environments because you can't disable interrupts for whole processors. Fine. Another hardware support is spatial machine instruction. Fine. Now, here we need to spend some time. Can anybody explain what is instruction cycle? Anybody?
So it is a process of fetching, decoding, executing the instruction.
So you are saying fetch,
And
decode,
executing,
execute, write
and
back,
write back. Yes, sir.
write back. So these, what are these known as? Machine cycles. So just revise these things, okay? So instruction cycle, machine cycle, and then everything else. Just revise these things. Now I'm saying that if anything can get completed in one instruction cycle, if an instruction can be completed in single instruction cycle. If anything can be executed in one instruction cycle, can it be interrupted? If I say there are 4 or 5 or 6 lines of code, and if I somehow, with the help of hardware, execute this in single instruction cycle, can this be interrupted?
No, sir.
Because interrupts can only be handled after completion of an instruction cycle. Instruction cycle cannot be interrupted in between. So these type of instructions are known as atomic instructions. Which are or atomic operations which are completed in one instruction cycle with the special support from the hardware. Special machine instructions performed in single instruction cycle, and because they are performed or executed in a single instruction cycle, they are not subject to interference from other instructions. So there are two types of these instructions: reading and writing, and reading and testing. Test and set instruction and exchange instruction. The important point here is that these instructions are performed in a single instruction cycle so as to avoid the interrupt and make them atomic. So this is test and set instruction. Fine. This is test and set instruction which takes a integer variable as an argument. If I equal to 0, it will make I equal to 1 and will return true. Else, if I equal to 1 already, it will return false. This entire test and set function is carried out atomically. It is not subject to interruption, means switching is not possible in between. It will be either executed or not executed. Some version of these instructions are available on nearly all processor families: x86, IA64, Spark, /390, etc. And most operating systems take help of this for concurrency. So entire function, Boolean function, which because it returns Boolean values, test and set, is carried out atomically, which is not subject to any interruption. Having said that, just see the code. There is another instruction known as exchange instruction. Again, entire instruction is performed in single instruction cycle, where there are two variables, register and memory, one in register, other in memory. So what you are doing, you are taking another variable and exchanging the values. So whatever is in memory would be there in register, and whatever there in register would be there in memory. The instruction exchanges the contents of a register with that of a memory location using a third variable, temporary variable. Both Intel IA32 architecture Pentium and IA64 architecture Itanium contain an exchange instruction. So we have these kind of spatial machine instructions which can be utilized to provide mutual exclusion. Now, let's see the code. So let's see here. Here, bolt is initialized to 0. Bolt is a variable. You can have n processes, where n is number of process, bolt integer. When I say p int I means p, if I is 1, then it is p1. When I is 2, it is p2, means p1 process, p2 process, and so on. While true, while test and set bolt. First of all, let's see the function. So bolt is initialized to 0. Bolt is initialized to 0. So what will be happening in test and set instruction? If it is initialized to 0, it will be changed to 1 and true will be returned. If it is 0, it will be changed to 1 and true will be returned. So if we get written as true, then this whole thing will be false. So while loop will not execute and a process will be in its critical section. Now before entering into the critical section, as you can see here, bolt was changed to 1. Now at this point of time, when a process in its critical section, other process, suppose P1 comes, P0 is executing and P1 comes. P1 will do test and set, and now bolt is 1. So if you see test and set again here, because if it is 1, then return false. False will be returned and the whole this thing will be true and P1 will be waiting. P1 cannot enter. Later on, when P0 comes out, it will be making bolt again 0. And now other process can execute this while and can get chance to enter the critical section. Any confusions? Any confusions? Rajendra?
No sir, कोई confusion नहीं.
Okay.
So isn't it same as that the first solution we discussed?
Why? Why?
There we are also having that one turn variable, right? And with that we were using for the mutual exclusion.
Just check P0 can run again or not. P0 is also in race. Once P0 is completed, bolt is 0 again. If P0 is scheduled again, P0 can run. Yes or no?
Yes, I got it.
P0 is again in race, no? There, once P0 is executed, P0 cannot execute again until unless P1 is executed. Clear?
Yes, sir.
Now I'm leaving this exchange instruction for you people to study and how using exchange instruction we can provide mutual exclusion. I'm leaving this for you people to study by yourself. Okay. What are the advantages of having machine instruction for mutual exclusion? It is applicable to any number of processes, either on a single processor or multiple processors sharing main memory. It is simple than the software solution, easy to verify. It can be used to support multiple critical sections within a program. Use the hardware instruction and then work is done. Disadvantages: busy waiting. Again, starvation is possible when a process leaves a critical section and more than one process is waiting. You have to have a policy that who can get and access that while loop if one process is completed in its critical section. Deadlock. Now this is interesting. This is beautiful. Just see here. Just see here. Suppose P0 is executing using test and set. P0 got the chance. P0 got the chance and P0 is executing in its critical section. Suddenly P8 arrives in ready queue, which is having higher priority than P0. So who will get chance to execute? P0 will be out and P8 will start executing. But the problem here is P8 also wants to execute in this critical section. What will happen? Abhigyan got the problem?
No, sir. If it
A lower priority process,
yes, sir.
suppose there are two processes, P0 and P8. Both wants to use critical section, same critical section. Okay?
Yes, sir.
Piece of code. Initially, P8 was not there. P0 was scheduled, started execution. P0 was in its critical section. Fine. While it was executing in its critical section, P8 arrives. So scheduler has nothing to think. Scheduler will throw out P0 out and P8 will be scheduled. What will happen to P8? P8 will be blocked because P0 was inside its critical section. P0 could not complete its critical section and bolt was not again set to 0. P8 will be blocked. So even if it is having higher priority, it will not be able to execute before P0. Yes or no?
Yes, sir. It is.
If a low priority process has the critical region and a higher priority process needs that, the higher priority process will obtain the processor to wait for the critical region. It is ready, it will take the processor, but it will not be able to move ahead. It can only move ahead when P0 is scheduled and complete its critical section. P0 will not be able to be scheduled because it is having lower priority, and then this is a deadlock. Yes or no?
Yes, sir.
Okay. Okay, then we have some operating system and programming language support. There are many supports: semaphore, binary semaphore, mutex, some condition variable, monitor, event flags, mailboxes, spin logs. Many supports which are provided by either programming language or the operating system. Now we'll be seeing these approaches one by one. Please be with me. Fine. Semaphores. It is not a locking mechanism, it is rather a signaling mechanism, which can be helpful in locking also. Two or more processes can cooperate by means of simple signals. A process can be forced to stop at a specified place until it has received a specific signal. And for this type of signaling, spatial variables called semaphores, and either the support is provided by operating system or the programming language. Fine. In your programming tools lab, you would be doing POSIX semaphores. For signaling, a spatial variable called semaphores are going to be used. To signal via semaphore, there is a spatial primitive known as sem signal, where S is a semaphore variable. To receive a signal via semaphore S, process has to execute another primitive known as sem wait. Actually, these are two functions, sem signal and sem wait. We'll be seeing this. A semaphore may be initialized to a non-negative integer value. Sem wait operation decrements the semaphore value. If this value becomes negative, then the process executing the sem wait is blocked. Otherwise, the process continues the execution. Sem signal operation increments the semaphore value. If the resulting value is less than or equal to 0, a process which was blocked by sem wait operation is unblocked. So actually it is a structure variable, because we need to have a queue also for arranging the blocked processes on semaphore. So if we see semaphore, it is a structure variable where int count is the value, and then any queue type is a queue. Structure variable. So what is this sem waits function? It decrements s dot count, and if s dot count becomes negative, less than 0, the process which is executing or operating this sem wait function will be blocked and will be placed in s dot queue. What is sem signal function? It will increment s dot count. If s dot count is less than or equal to 0, remove a process from S dot Q. Which process? That's debatable. You can have any policy. And place process P on the ready list. Or it can be unblocked. Otherwise, it is blocked. So let's see the mutual exclusion by semaphores. So let me take the snip of this. And please be with me. So program mutual exclusion, number of process n, semaphore S is initialized to 1, means here I mean to say S dot count is initialized to 1. P in time is P0, P1, and so on. While true, so S is currently 1. When you do same weight S, this, suppose P0 gets a chance. So what it will do? It will decrement S equal to S minus 1. So it will become 1 minus 1 equal to 0. And see here, the process will be blocked only if S becomes negative. Right now it's not negative. So P0 can enter into its critical section. So P0 is here. P0 is executing in its critical section. Suppose P1 arrives and P1 wants to execute. P1 will come, execute this function, same weight again. And now S would be S minus 1. S is currently 0 minus 1 equal to minus 1. It is negative, so P0 is blocked. Sorry, P1 is blocked. Suppose P0 is still in critical section and P2 arrives. So P2 will also be blocked and S will become minus 2. P3 arrives, P3 will be blocked and S will become minus 3. So if S value is negative, so negative 3 means 3 processes are waiting, are blocked. So P0 comes out of critical section. It will execute same signal. So what is this? S equal to S plus 1 minus 3 plus 1 equal to minus 2. See the same signal function. If S dot count is less than equal to 0, yes, it is less than 0. Unblock a process. Any of this process can be unblocked. And as soon as it unblocks, you can see it is minus 2. Minus 2 means 2 processes are blocked. Now suppose P2 is unblocked by any mechanism. You can unblock P1, P2 or P3. If it is first come first serve, then P1 will be unblocked. Suppose P1 is unblocked. Now P1 will come and directly enter into critical section. P1 will not execute some wait again because P1 has already executed this function and P1's program counter is incremented. So P1 can directly enter into its critical section. When P1 comes out, same signal again, it will be incremented -1. P2 will be unblocked and P2 can enter. Are you getting my point? Is it clear to everybody?
Yes, sir.
Rajendra?
Yes, sir.
Everybody is clear about
Yes,
this?
sir. Yes, sir.
But the important
Yes, sir.
thing you people haven't raised. This sem weight and sem signal functions have to be atomic. Yes or no?
Yes, sir.
So operating system, architecture, programming language will ensure that the sem weight and sem signal functions have to be atomic. Means once they have started, they cannot be interrupted in between. ऐसा नहीं होगा कि डिक्रीमेंट किया और ये लाइन एग्जीक्यूट नहीं हुआ और स्विच हो गया. No, this is not possible. So sem weight and sem signal function have to be atomic. Fine. So in this way, using semaphores, which is a programming language or an operating system construct, we can provide mutual exclusion. I'm done for today because next topic will be some problems which we can solve using semaphores, so which will be taken on the next turn. If there are any questions, you people can ask.